Hello, hello. Hello. Hello.
Hello. Yeah.
ये सेकंड स्टार्ट हो रहा है या फिर अभी
हाँ हाँ yeah yeah we'll start in 2 minutes. Yeah. Okay, we'll start now. Good evening. My name is Ranjan Bora. I am PhD scholar at IIT Delhi, and I am one of the TA in this course, Biomechanics of Joints and Orthopedic Implants. This course is instructed by Professor Sanjay Gupta from IIT Kharagpur, and I have been taking tutorials on this course weekly from the starting, and today is the week 6 tutorial for week 6. In today's tutorial, first I will discuss the assignment, the quiz from the previous week, from week 5, and after that I will discuss some concepts from week 6, and after that I will solve some numerical problems. So first, I will discuss the quiz from the previous week, week 5. So this was the first question in the quiz for week 5, like what is strain? I hope you know the answer. What is strain? Okay, before starting, I want to ask, have you gone through my previous week tutorial, which was uploaded on YouTube? Have you watched that video, last week tutorial? Okay. It is uploaded in YouTube, and the link for that video you will find on the NPTEL website. Like in the left side, you will find problem solving sessions. In that link, if you click, you will see the link to watch that video.
sir, the ratio of change in length to the original length. It is this thing.
Yeah, yeah, it is change in length to the original length. Yes, you are correct. So in the last week, I discussed about stress and strain in a very detailed way, and I solved some numerical problems also related to stress and strain. So you can go through that video of my last week tutorial. So strain, you can see this rod. If we apply some load, then it will get elongated by a certain amount delta, and according to the definition of strain, and it is the change in length divided by the original length is known as strain. So B is the correct answer. Next question, the materials which have the dash elastic properties in dash directions are called isotropic. What is what will be the yeah in in isotopic material we have the same elastic properties in all directions. Which number measures an object's resistance to being deformed elastically when stress is applied to it? With which number we measure an object's resistance to being deformed elastically when stress is applied to it? Yes. So elastic modulus, this is the definition of elastic modulus, stress divided by strain. So we can see that if a material has a very higher elastic modulus, if a material has a very high elastic modulus, that means that we need a very large stress to deform it elastically, because stress is proportional to strain. So if this ratio is very high, that means stress will be very high, and it represents the resistance to being deformed elastically. That's why B is correct. Bone is dash in nature. Yeah. So this figure you can see the bone morphology of different regions. Like it is not same in all the regions. Like you can see these regions 1, 2, 3, 4, 5, 6. All these structures are different. That's why it is an anisotropic material. Deviatoric stress causes change in what does the deviatoric stress cause? Yeah, shape only. Yeah. Mm, deviatoric stress means if it is an object and you apply a force in this tangential direction, means parallel to its surface, this surface, then because of this force, one stress will get developed, and because of this force, means there will be a change in shape. That means after applying, it will get deformed in this direction. The block will gets deformed in this direction. So this stress will be known as deviatory stress, because when this block gets deformed, then there is no change in volume. There is only change in the shape. Means this red one is the initial and green one is the final after applying this force. In last week's tutorial, I have discussed about this deviatory stress. You can go through that. Have you understood? Okay. And number of independent elastic constants for an orthotropic linear elastic material is? No, it is not 3, it is 9. Which of the following is not a property of any material?
Stress.
Yeah, stress.
Stress.
Anisotropic nature of proximal femur arises from the which groups? Yeah, you can see I have explained like this morphology is different in
Comprehensive.
yeah this morphology are not same in all the different locations of proximal femur. So these tensile and compressive groups, because of those groups, anisotropic nature arises. The fabric tensor is a dash which characterizes the geometric arrangement of the porous material microstructure.
Symmetric second right tensor.
Yes.
Sir, the previous questions, can you please explain, sir?
Yeah. Mm,
Thank you.
Again, this fabric tensor, I think it is there in the slide, right?
Yes.
Means I hope it is 6 by 6, 6 by 6 matrix, if I remember it correctly. Is it 6 by 6 or 9 by 9? So symmetric means, see, you know the matrix, right? What is a symmetric matrix? Means I will give you an example of symmetric matrix. This is a symmetric matrix. That means uh, this uh, this is mirror image with respect to these diagonal elements. These are the diagonal elements 1, 7, and 9, and 5 is this element 5 is mirror image of this, and this element 2 is mirror image of this, and this element 4 is mirror image of this. So this is known as symmetric matrix. So fabric tensor is a symmetric. That means these elements these elements are same, which are the mirror image with these diagonal elements. And the second, rank means rank is a property of a matrix.
How it is mathematics, sir? Please, I don't understand. How we can say it is mathematics?
Yeah, again I need to go the derivation. I don't have the derivation right now. I can give you the link in the Q&A section after the class if it is okay. Is it okay?
Okay.
Yeah, because this means these derivations are already there in a research paper, and sir has also taken these contents from some previously published articles. So I haven't gone through that research paper, so I need to see how it is coming as symmetric second rank tensor. Next question. Although computationally expensive, these models help in explicit modeling of trabecular bone.
KF micro SU.
Yeah. And how it is computationally expensive?
Required machine. Laboratory needs highly digital machine.
Yeah, we need very fine mesh means and high element. Yeah, because of the fine meshing, the number of elements counts are very high, and that's why we need a very powerful computer. So it is computationally expensive. Yes, in millions. Stress is defined as
External source per unit area.
no. Stress is internal resistive force per unit area. So you can see means in this rod we apply a force P at both the ends, and now if we take a section, that means if we cut this rod along this plane, and this section is represented here, because of this force P, there will be some resistive force which will get developed in these directions, and the magnitude of those resistive force will be equal to this P which is applying. So, and stress is, this is the definition of stress, this resistive force per unit area. A is the cross sectional area. Based on the given stress tensor, which is the first invariant.
Please explain this.
Yeah, see, first invariant, we have seen what is first invariant. We represent by I1, and it is uh, in a stress tensor we have sigma xx, tau xy, tau xz, sigma yy, tau yz, and sigma zz. And we know it is also symmetric, so it will be tau xy, it will be tau xz, and it will be tau yz. So what is first invariant? I1 is sigma xx plus sigma yy plus sigma zz. It will be 1 plus 8 plus 1, 10. So D is the answer. Is it clear?
Yes, sir.
Okay.
You can go ahead, what if it motion, if we change the position and we have to get it the second variant with that.
Sorry, I didn't get your question.
If we change the position, if the motion they mention second variant, which is the second variant.
Second invariant is uh, it is these formulas are already there in the slides. This is the second invariant. You are asking this, right?
Yes.
Okay. Next is apparent density is the dash per total volume of the tissue sample. Yeah, it is mineralized tissue mass A. What is the density of cellular solid divided by the density of the solid? Yes, it is relative density. And we know that bone is a porous material, and bone contains two phases. One is solid phase and another is fluid phase. The solid phase of bone composed of mineralized bone tissue, and the fluid phase composed of blood vessels, blood, marrow, and interstitial fluid. And here, relative density is the density of cellular solid divided by the density of solid. Endurance limit is the stress level below which an infinite number of loading cycles can be applied to a material without causing. Yes. Do you know what is endurance limit?
And limit, I think variable limit which can be a so
Yeah, so this is the plot of stress and number of cycles. Like endurance limit comes from the fatigue of any material, and we do one experiment to find out the endurance limit for any material. And what we do, we apply some stress, and we see at what stress, means after how many cycles the material is getting failed for a particular stress. So if we plot those values, means for the failing stress with respect to the number of cycles, we'll find that, means if we apply a stress below this dashed line, means if we apply any stress, then we'll get infinite number of cycles for that material, and this limit is known as the endurance limit. Means the material can withstand the stress up to an infinite number of cycles if the stress value is below this level, below this particular endurance limit. So C is the answer, fatigue failure. Next is based on the given stress tensor, which one of the following options is a principal stress? What is the answer for this question? Anyone?
What are you guys doing?
2 is the answer, sir, but I don't know why 2 is the answer.
No, 2 is not the answer. See, you know the definition of principal stress, right?
Sorry, B is the answer.
Yeah. B is the answer. So the definition of principal stress is means if in a plane, if in a plane there is only the normal stress and there is no shear stress in that plane, then this normal stress is known as principal stress. So is it clear? The definition means if in any plane there is only normal stress acting on the plane and there are no shear stress components acting on that particular plane, then that normal stress is known as the principal stress.
Okay, so the answer is B.
Yeah, so you can see like this first row and first column means this sigma xx is 7, then tau xy is 0, tau xz is 0, and so which plane it is representing? It is representing the x plane, right? So this is the x plane and there is only a normal stress which is 7, which is acting in this x direction, and this is y direction, this is z direction, and there are no shear stress in the y direction 0, and there are no shear stress in the z direction 0. So this 7 is a principal stress. That's why B is the answer.
Okay, sir.
Okay. Okay, next question is the tendency of a solid material to deform permanently under the influence of persistent mechanical stress?
Can you explain this chart?
Hmm. Like you can see from this plot, it is a plot of creep, means if we means this is the plot of variation of strain with respect to time. Like if any material we apply some instantaneous strain and means if any material we apply a continuous mechanical stress, means persistent mechanical stress, then what happens? We can see some instantaneous strain which will get produced in the material, and after that the strain will increase gradually with respect to time, and this strain is known as creep strain. And and after a certain time there is some elastic recovery in the material, means the strain we apply, some strain will get recovered, means elastic means it is again instantaneous, and an elastic recover, and there are some inelastic recovery, that means strain will recover after a means after a certain amount of time, it will not be instantaneous, and after a recovery some strain remains in the material permanently. There are some permanent deformation in the material. You can see this permanent strain, and the question is talking about deform permanently under the influence of persistent mechanical stress. And this plot is coming from experiment. Again, people have people have done the experiment on some material, like they apply, they take a material, they take a sample and they apply continuous mechanical stress, and after recording the strain, if they plot the strain with respect to time, they can get, they got this type of plot. So this experiment was known as creep, and means creep is the property of the material. They have named this property as creep for that material.
So suppose if a party of material doesn't amount amount when it will apply. It takes some time.
Yeah, yes. Do you have any doubt? Okay. Stress is a, which order tensor stress? Yes, second
Second
order.
order.
Yes.
Can we elaborate this question? How is second order test?
Yeah, means see, to define a stress, we need how many, means how many component we need to define a stress. Like we can say, so this is the definition of stress, and how many, what are the parameters we need to define this stress.
Stress means
Sorry.
applied force per unit area.
No, that is the definition of stress, but this is the representation of stress. To represent stress, what are the parameters we need?
Uh, First, change the shape of object.
No, see, this is the notation of the stress. Like in this, we have x and y. What does x represent? Yeah, x represent the plane and y represent the direction. So we need two parameters to represent the stress. That's why we call this stress as second order. Means for a three-dimensional object, for a 3D object, 3D element, we can say 3D element of stress. We have seen we represent the stress using 3 by 3 matrix for this particular element, like say stress in x uh, direction, z direction, then shear stress on the x plane in y direction, x plane in z direction. So means we need 9 parameters to represent a stress for a 3D element, and because of that it is known as second order. Because how do we means how do we get to know that we need the 9 parameters to represent the stress for a 3D element? There is one formula which is this represent the number of elements. N represents the order, how what is the order of the tensor. So for stress it is second order, so 3 n will come as 2, so 3 square will be 9. That's why we need these 9 components. Is it clear? Next is modulus of rigidity is the ratio of dash to shear strain. Yeah, it is the ratio of shear stress to shear strain. This is shear modulus. This modulus of rigidity is also known as shear modulus. This is the shear stress and this is the shear strain. Due to the viscoelastic property, the stiffness and strength of bone dash in with dash in strain rate. What is the answer? Yeah, B. You can see this plot is in the slide. So this epsilon 1 dot is the strain rate and it is greater than epsilon 2 dot, and you can see what is the stiffness. Stiffness is the slope of the stress strain plot. So this slope is higher than this slope. That's why means if we increase the strain rate, there is an increase in stiffness and also the strength, means the stress at which the material will get failed. So you can see this value is relatively, this stress is relatively higher than this stress. So both the stiffness and strength increases with increase in strain rate. So is it clear? Okay. So in the week 6 content, means sir has discussed about finite element and method, like uh, how we can use the finite element method uh, to simulate any loading conditions for any bone. Like we want to see what is the impact of the hip implant on the femur bone uh, after the patient after the hip implant is implanted to the femur bone. What will be the effect of the hip implant to the femur, like because of that implant, will there be any stress shielding in the surrounding bones. So all those analyses we can study using the finite element method. So in today's tutorial, I will briefly tell you what is finite element method, like the mathematical algorithm behind any computer simulations. Because in the slides sir has shown like the computer simulation results, means after performing the finite element method, what are how are the stress distributions in any particular bone. So I will just briefly tell you about the mathematical algorithm of finite element method. So it will be relatively easy for you to understand, or if you want to perform any simulation in any finite element software, you can do that. So the finite element method is a numerical method for solving problems on engineering and mathematical physics. And because physical systems in which involve complicated geometries, loadings, and material properties, it is not possible to obtain analytical mathematical solutions. So the finite element formulation results in a system of simultaneous algebraic equations for solutions. And in these figures you can see some already published result which involves the finite element analysis. So in this plot you can see this is a femur bone, this is the stress distribution in a femur bone, and this is the displacement, means the deformation in a femur bone. And it is a mandible. In the mandible, if there is any fracture in the mandible and surgeons used some plates, then they perform some finite element analysis to study the stress distributions, the effect of these plates on the mandible. So for those analysis we use the finite element method. Now there are different methods to derive finite element equations. There are mainly three primary methods. These are the first one is direct method or direct equilibrium method. Second one is variational method or the principle of virtual work, and the third one is weighted residual method. In today's tutorial, I will briefly discuss about this direct method or direct equilibrium method. Now, what are the steps to solve any problem using finite element method? First step is discretize and select the element types. So in the finite element, from the basics, if it is a one-dimensional problem and we have some one-dimensional elements which are spring and bar element, we can use these elements to solve any one-dimensional problem. For two-dimensional problem, we can use triangles or quadrilaterals to solve any problems. And these points you can see, these are known as nodes and these are known as elements. So you can see we can, in a triangle we can have 3 node or 6 node. Similarly, in a quadrilateral we can have either 4 node or 8 nodes, means node in between its length, each side of the quadrilateral. And for 3D elements we have the tetrahedrals or regular hexahedral or irregular hexahedral. And the biomechanics problems which I shown in the previous slide, we use these tetrahedral elements to solve the biomechanics problems. In a tetrahedral also you can see this 4-noded tetrahedral, or this is the 10-noded. You can 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the 10-noded tetrahedral element. And step 2 is we select a displacement function. The displacement function can be either linear, quadratic, or cubic. Step 3 is we define the strain displacement and stress strain relationships. Like we can define strain as change in length divided by the original length, and stress we use the Hooke's law, which is sigma equal to E times epsilon. E is the Young's modulus. And step 4 is we derive the element stiffness matrix and equations. And next step, we assemble the element equations to obtain the global or total equations, and we substitute the boundary conditions. This is the global equation. This is the global force vector, global stiffness vector, and global displacement vector. And then after substituting the boundary conditions, we solve for the unknown degrees of freedom or the unknown displacements. This is the global matrix. And in the next step, we solve the element strains and stress. And in the final step, we interpret the results. So in any computer software like NCS, Abacus, we have to solve any finite element problem. All these steps are followed from the step 1 to step 7. Means all these algorithms are already there in the software. Now today's tutorial I will discuss only about the one-dimensional spring element, because the two-dimensional and three-dimensional problems becomes very complex. We need more time to solve, and I will not cover that in our discussions. So for a spring element, again the first step was to select the element type. We know the element type is already spring. You can see this figure. This is a spring, and these are two nodes. 1 and 2 are two nodes, and K is the stiffness of the spring. U1 is the displacement at node 1, and U2 is the displacement at node 2, and F1 is the force acting at node 1, and F2 is the force acting at node 2. Second step was to define the displacement equation. Here you can see this is the displacement equation, delta equal to U2 minus U1. And the third step was to define the strain displacement stress strain relations. So for a spring, we know this relation, force equal to stiffness times the elongation. Here delta is the elongation, which is U2 minus U1. Now next step is derive the element stiffness matrix and equations. So it is not
So how can we predict K?
sorry, predict what?
K.
K. Yeah, K will be given to you. Means K is the property. K is the property of the spring. This K.
It would say node and then there is a method to predict K.
No, it will be mentioned because it is a spring property. Like if you have any spring, you need to know what is the stiffness of the spring, and it will be given. Okay, so we have seen this equation K U2 minus U1 equal to T, and comparing nodal forces, what will be F1? See, F1 was in this direction, right? So F1 will be minus T and F2 will be T, because F2 was in this direction. So now K U2 minus U1 equal to minus F1E, K U2 minus U1 equal to F2E. So The resulting equation, it can be written in matrix form as in this form. So this matrix form is coming from these two equations 1 and 2. You can see k is common, k is same for both the equations, and here it was minus u1 plus u2, and in the second equation it was minus u1 plus u2, and in the right side we have one minus. So if we bring the minus to the left side, it will become plus u1 minus u2. Here plus u1 minus u2, and in the second equation minus u1 plus u2. Forces are F1 and F2. So above equation is the element level equation for a spring. This thing I have explained. So you can represent this equation like this. Next step is to assemble the element equations to obtain the global equations and introduce boundary conditions. Now global matrix equation is obtained by assembling the element level equations. Here k u equal to f. K is the global stiffness matrix, u is global displacement vector, and f is the global force vector. Now how do you know the size of global stiffness matrix and size of global force vector? There is one formula here, like total number of degrees of freedom in the system is degrees of freedom per node into total number of nodes. So for a spring element we have two nodes, and degrees of freedom per node is 1. Like this node can displace only in the horizontal direction, and the second node also can displace only in the horizontal direction. So for a spring element it will be degrees of freedom per node into total number of nodes is 2, it will be 2. So what will be the size of global stiffness matrix? N by n, this n. For a spring element it will be 2 by 2, and size of global force vector n by 1, that will be 2 by 1. Now next step is to solve for the nodal displacements using this expression f equal to kd. In the next step we solve for the element forces. Now I will solve one problem based on the concepts which we have seen so far in the finite element method. In this problem, these three springs are assembled like as shown in the figure. You can see these are the spring constant k1, k2 and k3. For these three springs are given. Now for the load and boundary conditions, find out the nodal displacements and force in each spring. So we have derived the element level equation for a spring, which was k 1 minus 1 minus 1 1 u1 u2 f1 f2. So for the first spring, what will be? First spring, the element level equation will be See, for the first spring, these are the nodes 1 and 2, and the spring constant is given as 1000. So in this matrix, if we put 1000 here, it will means multiplying this matrix with 1000, and u1 and u2 are unknown, f1 and f2 are also unknown. u1 is known, u1 is 0, because you can see this and this fixed, right? So this node, and it is fixed, so it can't display, there is no movement in this node 1, so displacement of node 1 is 0. This is known to us, but u2 is not known. Because of this applied force of 100 Newton, there will be some displacement at the node 2, so we have to find out u2, and f1 and f2 are also not known to us, so we have to find out this f1 and f2. So this is the equation, element level equation for first spring. Similarly, for the second spring, it will be second spring also, it will be 1000. For the second spring, then nodes are 2 and 3, so it will be u2, u3, and what are the forces? f2, 3. Third spring, it is 3000. Node numbers are same, 2 and 3. That's why I have written here u2 and u3, and force will be f2 and f3. Now what was the next step? Next step was we need to find a global equation, means global stiffness matrix. That means we need to find out these equations. So how we can find out these equations? We need to assemble these three equations. And how we'll assemble? You can make one table here, like this is element and node connectivity. So for element 1, the node connectivity are 1 and 2. Element 2, node connectivity are 2 and 3. And element 3, node connectivity are 2 and 3. So now we need to do the 3 by 3 stiffness matrix. So, or we can number, we know that 3 by 3 matrix, there will be 3 rows and 3 columns. So we can number first row, second row, third row, first column, second column, third column. So first element, node connectivity is 1 and 2. That means for the first element, uh, it will come in these positions, 1 and 2 positions. What was it? 1000 minus 1000 minus 1000, 1000, 1000. And second element, node connectivity was 2 and 3. So it will come in these two positions. This position, this. Because 2 and 3 means we do the second row and third row, and second column and third column. what was it was 1000, so it will be plus 1000 minus 1000 minus 1000 and 1000. And for the third element also the node connectivities are 2 and 3, 2 and 3, so it will again come in these positions 2 and 3, 2 and 3. Third spring it was 3000 minus 3000, so it will be plus 3000 minus 3000 minus 3000 plus 3000, and the remaining elements will put as 0. So this is the stiffness matrix. Next is uh, displacement matrix will be u1, u2, u3, and force matrix will be, again we'll do same, means it will be f1, f2, f3. So is this clear how you have found this global matrix? This is the global stiffness matrix, global displacement function, and global force factor. Any doubt in this? Have you understood it?
Sir, could you explain how we combine this equation?
This stiffness matrix.
Yes, 2 and 3.
Yeah, means for this is the global stiffness matrix, and in global stiffness matrix we assemble the element level stiffness matrix. So for the first element, means this is the element level stiffness matrix. These are the element level stiffness matrix, k1, k2, and k3. Now uh, we see here the node connectivity. Like you can see, this is the first element, it is connected with node 1 and 2, and the second element it is connected with node 2 and 3, and third element also connected with the same nodes 2 and 3. So in the global matrix, means um, we we position the node, means we position the node numbers with the row numbers. Like for the first element you can see, means the first element node connectivity was 1 and 2, so we'll put the element level stiffness matrix for the first element in their corresponding positions with respect to 1 and 2. So this is a 2 by 2 matrix, so we'll put that matrix in this 1 and 2 position. Is it clear? Yeah. And same second and three element, for the second and third element also we'll follow the same method. Like these are the node connectivities were 2 and 3. So we'll put this two matrix to K2 and K3, means in these positions 2 and 3. So, and while putting, there is already some terms from the first element 1000. So we'll just add. We'll add this 1000 from the second element and this 3000 from the third element.
Okay. So 2 and 2, we add the first element and second element.
Yeah, means these 2 and 3, these are for the second and third elements.
Okay.
Okay, so we found this global stiffness matrix, which is 1000 minus 1000, 0. It will be 5000 minus 4000, 0, 4000, U1, U2, U3. We can write it as F1, F2, F3. Now next step is we apply the boundary conditions, and in the boundary condition it is given U1 is 0 and the value of F3 is given. F3 is 100 Newton. So in the next step, what we do, we uh, eliminate the corresponding rows and columns, means for the displacement which are 0, we eliminate corresponding rows and columns. Means here the first displacement is 0, so we'll eliminate this row and this column from this matrix. So after eliminating, how it will be 5000 U2, U3, F2, 3. So we have just removed this first row and first column from both the sides. Then we got this 2 by 2 matrix, this 2 by 2 matrix. And here F2 is not given in the question. You can see there is no force which is acting at node 2, so F2 is 0 and F3 is 100. So if we simplify these equations, you will get 5000 U2 minus 4000 U3 equal to F2 is 0 and one more is 4000 U2 plus 1000 U3. F3 is 100. Now if we solve these equations, we will find out the values of U2 and U3. From 1 we can 4000 U3 is 1000 U2. From 2, if we substitute 5000 U2, it will be 1000 U2 equal to 100. So from here U2 is 0.1 meter, and from this equation U3 will be 5 by 4 into 0.1. It will be 0.125. And u1 was already 0, so we know values of u2, u3. u1 is known to us. We don't know this value of f1. How we will find out the value of f1? Simply we will write means from this matrix we can write 1000 u1 minus 1000 u2 equal to f1. So u1 is 0, f1 is minus 1000 u2. So 0.1, it is minus 100 Newton. Now we have find out, like, if it is f3 is acting 100 Newton, then f1 minus, we have got minus 100. That means it is acting in this direction, 100 Newton. Yeah, we removed f1. See, if we simplify this matrix, then this was the first equation we got. Similarly, if we simplify the second equation, which will be 5000 u2 minus 4000 u3 equal to f2. And now if we simplify the third equation, it will be u2 plus. So is this clear? We have found these three equations from this matrix. Because u1 is 0, I have not written the u1 term here. I have written u2, u3, and f2 and f3. So these equations are clear, right? You got understood. Is it understood how we have found these three equations from this matrix? From this matrix, we have found these three equations. This was equation 1, equation 2, and equation 3. Is this understood? Arindam?
Yes, I was just wondering in the next slide, you remove the F1 part. Uh,
Yeah.
so that means since U1 is 0, that
Hmm.
is the reason F1 was removed, or was there anything else?
Yeah, means you have understood these three equations now, how we got
Yeah,
these
yeah.
three equations.
This part is fine.
Yeah.
But I was just thinking about the in the next slide when you reduce this thing, since U1 was 0, you
Hmm.
remove the first row, first column, also the U1, but also there was no F1 as well. So that's why that is the part I'm on. Yeah, here you can see there is only F2 and F3.
Yes, yes.
So I was just wondering what happened to F1 then. Is it because U1 is 0 that is why you did not consider F1, or what was it?
Yeah, like you can see these two equations. These two equations, if we now represent in matrix form, how we represent these two equations? Means if we represent these equations in matrix form, we'll get this form, right?
Yes, yes.
So means these were some intermediate steps which I didn't show. Like first we simplify these equations, then we will get these three equations, and we will take only the second and third equation to represent in the matrix form. So we have picked these two equations and we have represented it those two equations using this matrix form.
Hmm.
Yeah, so that's why f1 is not coming here, because we have taken this second and third equation only.
Okay.
Okay. Okay, so we have found out the nodal displacements. Now we need to find out the force in each spring. How we will find out that? Force in each spring will be, for first spring, it will be K1 U2 minus U1. K1 is given as 100, sorry, 1000. U2 is 0.1, so it will be 100, and F2 will be K2 U3 minus U2. It is again 1000. U3 is 0.125, 0.1, so it will be 0.025, 25, yes, 25 Newton. F3 is K3, K3 is 3000 into 0.025, so it will be 75. So these are the forces in each spring. I think it is clear to you. Do you have any doubt?
So that capital F3 is the nodal force, that 100 Newton, that is applied at the third node.
Yeah, yes.
And these small f's are the forces applied on the spring.
Yeah, yes, yes. Yeah, these are the forces in each spring because of this applied force 100 Newton.
Okay.
Okay. Okay, so now uh, I will give you the software demonstration. Like in the slides, Sir has mentioned about the mimic software, like how we can use the thresholding options to segment to perform the segmentation if we have the CT scan data. So I am going to show that. Is my screen visible? Hello, can you please confirm?
No, it's not visible.
Okay.
Yeah, it is now.
Okay, can you see this folder CT data? I think it is visible, right? CT data folder. Okay, so this is some CT scan data from a patient. Like we receive this data in the form of DICOM images. These are the DICOM image files. Means while we do any CT scan of any patient for any particular region, we get this data from that software. So we use this data to segment out the bones. So this is the CT scan data for a skull, and in the skull we know that in the skull there are mandible bone, hyoid bone. So I will just going to show that what are the various bones which are present in skull. So this is a mimic software. Here we can use those tools. You can see these are the tools segment. There are various tools are here in this software. So now I will import those files which are the CT scan data of a skull. I have selected that folder. Next, click on open. There are some images which are not some errors in some images. Those images will be rejected by the software. So you can see we have imported the CT scan data. So in this software we can see three planes, like this is the coronal plane, and then axial plane, and the sagittal plane. Now if you want to see the 3D, so this was the patient from which we have got this data. Now what I will do, I will create one, go to the segment tool, and I will create one mask, new mask.
Okay.
Yeah, you have any doubt? So after clicking the threshold tool, you can see these are the Hounsfield unit. These are known as Hounsfield unit, and in the drop down you will get different already predefined threshold sets. Like we have bone, then soft tissue, enamel, compact bone, muscle tissue, skin tissue, tooth, prosthesis. So I have selected a bone here because we want to segment out the bone. So if we, after selecting the bone, you can see that the Hounsfield unit is already defined, like it is from 400 to 3071. So it is taking as 226 minimum. So if we click on OK, then we got this green colored, we got this bone from the CT scan data. So you can see what we have. We have this mandible, then skull, and this bone is the hyoid bone, and some part of the cervical spine. Now we are interested in to separate this mandible from the skull. You can see now this mandible is attached, connected with the skull. So we want to segment out this mandible. So how we can do that? There are various tools here, like split mask, region grow. I will use this split mask tool. I will use this split mask tool to segment out the mandible from the skull, and I will select this sagittal plane. So you can see this sagittal plane. These are various images of the CT scan data. So now we need to locate the first image where the mandible is starting. Like you can see, if we slide over, you can see this portion. If you can see my cursor, this blue color cursor, this portion is the mandible, cross section of a mandible, cross section of the mandible. So now if we slide over it, you will see the various cross sections of mandible in the green color, like this portion, and this portion with the mandible, some teeth are coming, like this. We are coming to the means from left side to the right side. This is the right side. Now if we scroll upward, we'll see, means we'll traveling from the right side of the CT scan image to the left side. So what we need to do in the split mask tool, you can see there are two regions. So we are interested in two regions. The region A means we want to separate the mandible. Region B is from the skull. So we need to select the mandible. In this image. In these images, means by skipping some image. Like if we select this, you can see this portion is the mandible portion. If we select this mandible here, then we can skip some images and then jump into 2-3 images forward. Then we will select this image. After that, again we will jump 2-3 few images. We'll select this mandible section, and likewise means we'll select the mandibles by skipping some images in between. So now I will start. Just we need to locate the first image where the mandible is starting. You can see this is the mandible. This is the condyle of the mandible, and it is starting from this image. You can see this little portion. So I will increase the diameter of the brush, and I will select this. You can see this green colored portion is turned into blue. and after that I will skip few images, then I will select this, and again it is turned into blue. Increase the diameter a little bit. I will skip few images and select it. Will select mandible. Select this. I have selected the mandible. Next here, some portion of the mandible on the condyle, and selected the remaining portion. Again this portion, this portion. Next here we will select the tooth also, because tooth is connected with the mandible, the lower teeth. We will traverse from the left side to the right side, and we will select few images of the mandible by skipping some images in between two images. This is the mandible. Now this is the end slide of the mandible. You can see after this there are no mandibles coming in the slide. So this was our end slide. Now we'll select here region B. Now we'll select the remaining portion, which is skull. So I will increase the brush diameter. Now to select the skull, what you need to do, you will need to select the skull in those images only in which we have selected the mandible. That means in those slides we have not selected the mandible. We will not select the skull as well. Means in those slides we have only selected the mandible, and we have colored the mandible with blue. In those slides only we need to select the skull. So here, since we have selected the mandible and we have colored the mandible as blue, here I will here you don't need to select the whole skull. You have to just click once. Sorry, you increase the diameter and you click once. You can see that the skull is turned as red. You can see this mandible is still blue. Again, you have to very careful. You have to see the slides in which we have turned the mandible as blue. Only in those images we need to click this click with our mouse, and then this skull will automatically get turned into red. So now next we'll select here, select here. select here. Then select here. You don't need to miss any image. If you miss any image, then it will not create our, it will not segment, I means it will not get completed. So we are done. Now we have selected both the regions. The region A was mandible and region B is skull. Now we'll, if we click OK, you can see two two regions will be, so you can see here we have separated, the mandible from the skull. So this is the mandible. We have separated the mandible from the skull, and now we can click on calculate part. Okay, so this region is coming here. Now from this we can export this as STL file. Like you can see, we can click on this export STL. Then we can generate the finite element mass of this mandible. Then we can do any finite element analysis using this mandible. Okay, so I think, do you have any doubt, Durgaras?
Which was the software? How big is it available for everyone or?
No, it is a licensed software, so means it will be not available for you. There is similar software, Thematic. You can download that software.
What is the name, sir?
Yeah, it is three. Oh, sorry, it is 3D slicer. 3D slicer.
Okay, sir.
Yeah, you can use that software. That is freely available. 3D slicer.
Okay, sir.
Okay. So we can leave now if you have no doubt.
Okay, sir. Thank you very much, sir.
Yeah, thank you. Thank you for joining.